Hello everyone and welcome to the second block of your module on artificial intelligence and games. So I'll start today by introducing you to reinforcement learning. But before I do that, I want to talk a little bit about intelligence. So many people, even experts, would say that we don't have a good definition of intelligence, but I strongly disagree with that. I think we have an excellent working definition of intelligence, meaning that we have a definition that we can, in practice, use to develop intelligent agents and algorithms. Um, so the definition I'm talking about is the following. Intelligence measures the ability of an agent to achieve goals in a wide range of environments. Now, this definition does not come out of thin air. Shane Legg in 2008 collected a large set of definitions of intelligence and found out that almost all of them could be reframed to agree with this definition that I'm presenting to you. So let's take a little look at each of the components of this definition. So intelligence is a measure. So intelligence is not, something is not either intelligent or not. The intelligence of something is on a scale, on a spectrum. Um, so intelligence measures the ability of an agent. So in order for us to be able to measure intelligence and to talk about intelligence, we have to be looking at an agent. So we have to be looking at something that acts. So we don't care about, for example, a potentially omniscient agent that knows everything about the world but has no interest in acting in the world, because you can only measure intelligence through the actions of an agent. Furthermore, this agent has to have goals. So intelligence measures the ability of an agent to achieve goals. So we are also not able to measure the intelligence of, to compare the intelligence of different agents if they have different goals. And this is a common mistake that people make when they try to compare the intelligence of different people in real life, for example. So you cannot really compare two people regarding their intelligence if they have different goals. Having different goals can very often explain why people behave differently in the same situation. So finally, intelligence measures the ability of an agent to achieve goals in a wide range of environments. So it's not sufficient for an agent to be highly specialized to a single environment to be called highly intelligent. An agent has to be able to adapt and work in a wide range of environments to achieve goals. So that's the definition of intelligence that I really like. So as you can see, this definition of intelligence requires flexibility and requires activity. This definition is incompatible with colloquial usage. That's not the way most people use the word intelligence on their day-to-day. However, this definition does allow, it can be formalized given some additional assumptions. So you can bring this definition from this high-level intuitive perspective that I've just presented to you to a mathematical definition that is very precise. Furthermore, this definition also enables researchers to understand their role within the task of developing intelligent systems. So, for example, if you work on natural language processing, you should be aware that whatever modules you develop have to be integrated into a system that acts in the world at some point for it to really be to be considered intelligent in some way. Now, even if you disagree that this is a good definition of intelligence, I would argue that highly intelligent agents, according to this definition, are useful. So even if you don't want to call my definition intelligence, you should probably still agree that having agents with these kinds of capabilities will be useful in the real world. So why am I talking so much about intelligence? Well, reinforcement learning, as I see it, is the natural technical framework through it that can be used to study artificial intelligence. And as you see, basically all the elements that from my definition of intelligence from earlier appear in the reinforcement learning setting. But now the goals, as I mentioned, will be defined through reward mechanisms. So let me step back a moment and finally define what reinforcement learning is. So reinforcement learning is the study of the interaction between an agent and an environment. So you can think of the agent as, for example, a robot, or you can even make an analogy between an agent and a person. You can think of the agent as a computer making automatic decisions in some environments. So the environment could be either the real world, it could be a simulation of the real world, it could be a closed system that waits for decisions from the agent. Any closed system that awaits for decisions from the agent. So how does the agent interact with the environment? So an agent will observe at a given time step, and these are discrete time steps, so you can imagine that time starts at 0 and then is increased to 1 and is increased to 2 and so on. And at each of these time steps, the agent will receive a state, and the state is a representation of the state of the environment. So the state really represents what you would naturally associate with a state. So the agent needs to know how does the environment look at a specific moment in order to be able to choose its action. So that's how the agent responds to a state from the environment. The agent responds with an action. So for a given situation, the agent must make a choice. And the environment will then respond to this action with a new state, so a state for the next time step, and with a reward. The agent will then observe this new state and take a new action. The environment will respond with a state and a reward. The agent will take another action. The environment will respond with another state, and so on for a number of time steps that you can imagine is fixed for now. Now, the goal of the agent in this setting is to maximize the sum of rewards. So the agent wants to maximize. So the agent wants to maximize the sum of rewards that it observes until some final time step that I'll denote by capital T here. So that's so as I mentioned, goals have to be defined through reward mechanisms in this setting. But that's basically the only thing that brings something different to this definition. So let's look again at this definition. Intelligence measures the ability of an agent to achieve goals in a wide range of environments. So we could reformulate. So basically, we could also say that a reinforcement learning agent is intelligent if it's able to maximize rewards in a wide range of environments. So if the agent is highly flexible, no matter what environment it's presented with, it's able to maximize rewards and as such achieve goals, then the agent should be considered highly intelligent. So reinforcement learning certainly is not the only way to study artificial intelligence. However, it does make very explicit some problems that artificial intelligence are absolutely bound to face. So as an example, there's a problem in reinforcement learning called the exploration-exploitation dilemma, and any intelligent agent will have to face that problem. Humans face that problem regularly, and reinforcement learning makes it possible to study these problems very explicitly. So I hope that was a good motivation for study reinforcement learning for you, that for those of you who are interested in maybe researching artificial intelligence one day. Now let me go back and just once again mention the elements of reinforcement learning. So in reinforcement learning, an agent interacts with an environment during a sequence of discrete time steps. We've seen that. At each time step, t, the agent will receive some representation of the state, st, and I'll denote by S the set of all possible states of the environment. This set of states can be finite, it can be infinite. For now, we'll not worry about that. At a given time step t, the agent will select an action that I'll denote by at, and this action is taken from calligraphic A of st, which denotes the set of actions that are available in state st. Okay, so this S is the set of states. This A of st is the set of available actions at a given state st. One time step later, so after the agent takes an action in a given state, the agent receives the reward rt plus 1. So in state st, the agent takes action at and observes reward rt plus 1. So you can think about the sequence, the entire sequence of interactions as a sequence of state. So there was a state, there was an initial reward R0. At this point, the agent took action A0. It observed state S1. It observed reward R1. It observed reward action. It took action A1. It observed state S2. It observed reward R2. It took action A2, and so on. Okay, so this basically summarizes the entire interaction between the agent and the environment in reinforcement learning. Now there's a very important element that I did not make explicit yet, and that element is the policy pi. So a policy denoted by pi, not to be confused with the circle constant. So a policy pi is a function such that pi of SA represents the probability that the action at time step t will be A, given that the state at time t is S. So a policy simply represents how the agent behaves in the environment. So different agents may have different policies, meaning that they make different decisions given the same situation, potentially. So if you have, so again, a policy is a function, and it takes a state and an action, and it gives you a probability. Let's write it down as P for now, for taking a specific action in a specific state. So let's say that let's say, for example, that in a given state S, the agent is sure to take action A. In that case, our policy would simply say that the probability of in state S taking action A is 1. The opposite thing could also be represented by a policy. If in a specific state S, the agent would never take action A, we could represent that by pi of S and A being 0. However, a policy is flexible enough to allow us to make non-deterministic decisions. So maybe you have a state S, and you want to say that in a state S, you have 0.5 probability of taking an action, let's call it A1, and you have 0.5 probability of taking action A2. Now, why would you want to make non-deterministic decisions? Well, in some cases, the best thing to do is actually take um, a non-deterministic decision. Imagine, for example, that you're playing a game of I forgot the name in for that game. Imagine you're playing the game of rock, paper, scissors. I was just remembering the name Jock and Poe and not rock, paper, scissors. In that case, if you're playing um, against an opponent that takes random actions, the best thing that you can do, so an agent that randomly picks either rock, paper, or scissor, the best thing that you can do is also randomizing your actions. There's nothing that you can do in order to exploit that player, so you better be able to take random actions as well. Um, so this having a policy is just a very general way of representing um, how you behave in an environment. So a reinforcement learning agent is defined by its policy. So let me introduce the concept of discounted return. So initially, I mentioned that the agent is interested in maximizing the sum of rewards that it observes across time steps, but that's a bit of a simplification. So let's define the discounted return after a time step t as the sum of rewards that are observed after that time step. However, let's also suppose that each of these reward terms is scaled by a constant gamma, and gamma will be a number between 0 and 1, but that will be always below 1. Okay? So in other words, let's define this quantity called discounted return, and that is simply the sum for every time step from 0 to the sum for every k from 0 to infinity of the reward that you observed k steps after step t plus 1 of gamma to the k. Now let me go at this again. I think maybe this is not sufficiently clear yet. So let's suppose that I'm in a given time step t. I'm going to denote by ut the sum of rewards that follow time step t, so t plus 1, t plus 2, t plus 3, and so on, up to infinity. And I'm going to scale each of these rewards by a constant that for which I'll increase the exponent. So why am I not just summing? Why don't I just define the sum of the return as the sum of rewards until the end of time? Well, the problem is because I want to sum the rewards until the end of time, I have to guarantee that this sum converges. So in order for this sum to converge, one very simple trick is to multiply each of the terms in the sum by a constant taken to the power of how many time steps after time step t I'm looking at. Okay, so this sum you can show in this is a simple result from calculus that a sum of this form will always converge to a real number as long as the rewards are bounded, meaning as long as there's a minimum and a maximum reward, that this sum will always converge. But there's another interpretation, and maybe that will be easier for you to understand, of what this constant here represents. So basically the true role of this constant really is to make this summation of rewards seen from now time step t until the end of time. The role of this constant really is to make this sum converge. However, there's also an intuitive interpretation for this constant. So the interpretation is this: a reward received k time steps into the future, so k time steps after time step t plus 1, is only worth gamma to the k minus 1 times what it would be worth if it were received on the next time step. So because we are summing rewards and we are multiplying later rewards by a number that is between 0 and 1, excluding 1, up to some power, what's going to happen is that the rewards that come later in the sequence will have less of a value. So imagine, for example, compare, for example, let's say that gamma is 0.5. Gamma squared will be 0.25. So you can see that the reward for that will be observed in this case 2 time steps into the future will be worth more than the reward, than the same reward if it were observed 1 time step later. And similarly, you can think that this first reward here is multiplied by gamma to the 0, which is 0. So the next reward is worth the most to you. The reward that comes after that is worth less. The word that comes after that is less, and so on, until at some point the rewards really don't matter that much to you because they are so far away into the future. So this gamma factor basically controls how future-oriented the agent is. The closer to 1 this gamma is, the more the agent values rewards that come later, and the closer gamma is to 0, the less the agent values rewards that come later. So it's clear here that we are considering the sum of rewards until the end of time. But what if we wanted to just have an environment where the agent interacts with the environment for a fixed number of time steps, and then the interaction stops happening? Well, you can actually see that as a special case of this formulation here, because you can imagine that the agent interacts with the environment for a number of time steps. And after, let's say, capital T time steps, the environment produces a state that basically represents the end. And no matter what the agent does from that point on, the agent will remain at this end state, and the reward that the agent observes will be 0. So actually having an interaction that lasts for a fixed number of time steps can be just seen as a special case of an interaction that lasts forever, which is why we prefer this formulation in reinforcement learning, although it does require the use of a discount factor. And just one more detail, this discount factor could actually be 1 if we did guarantee that there is such a t after which the interaction between the agent and the environment stops, in the sense that the environment stays at the same state no matter what the agent does, and stays and always emits 0 as reward. So this case where the interaction lasts forever is the more general case, which is why we'll look at it in more detail. Okay, so the objective of an agent, as I've already mentioned in reinforcement learning, is to maximize the discounted return. So we will no longer talk about the sum of rewards, we will always talk about the sum of discounted rewards. So let me finally give you an example to make everything that I've said so far more concrete. So this example is a very traditional example. It's called a grid world. So there are many different grid worlds. This is just one example. And in this grid world, there is an agent, and this agent is a robot. And this robot is placed in a map. And in this map, the agent can take 4 actions. It can go left, it can go up, it can go right, and it can go down. Now, if the agent is in a state like this one, where there's no, where he's already at the end of the map and cannot go down, then the action go down will simply make it so the agent stays where it is already. Okay, so the actions that the agent can take are always the same. They are up, up, down, left, right. And if the agent is not able to make that move, the agent will just stay where it is after it takes that action. Okay. And in this grid world, there are 12 states. So we can, first of all, we can represent the 4 actions by 4 numbers. And that will just be for convenience. So maybe number 1 represents action up, 2 represents down, 3 represents left, and 4 represents right. That doesn't matter too much, but I just want you to realize that you can always represent, you can map a finite number of actions to a finite set of numbers, okay? Similarly, you could map the states in this environment to 12 numbers. So what would be the states in this environment? Well, the states could be just a description of where the agent currently is in the map. So maybe we want to number this state number 1, this state number 2, this state number 3, this state number 4, this state number 5. This would not be a state because the agent could never be in this position. This here represents a wall. So let's call this a state. Let's call this a state, state 7, 8, 9, 10, 11. Now I said there were 12 states. So where is the 12th state? Well, I forgot to mention this, but this environment basically behaves as follows. The agent is at a specific position. It can take actions, and upon taking the actions, it will move to the corresponding position, next position in this map. But once this agent reaches this state or this state, oh, and the agent will receive 0 reward for moving into any of these states. And it will always also receive 0 reward for moving into this state or for moving into this state. However, once the agent is in this state, wherever action the agent takes, it observes a reward of 1. And it transfers to what I called, remember, an absorbing state, which is the 12th state. And from this state, no matter what the agent does, the agent will be trapped here forever, and it will not obtain any more rewards. Similarly, when the agent moves to this state here, which is called a trap, the agent doesn't receive any reward. However, after it takes any action inside this state, the agent will transition to the absorbing state and stay there forever and not receive any more reward. So again, how does the environment work? Well, you have 12 states, 1 for each position of the board, and you also have this absorbing state. The agent has 4 actions in every state and go up, down, left, and right, and it needs to choose one of those actions. The agent doesn't receive any reward when it gets to a reward or when it gets to a trap, to a reward, sorry. The agent does not receive any reward when it moves to a go state or when it moves to a trap state. However, when it does take any of the available actions here, it will receive a reward of +1. And when it takes any of the available actions here, it will receive a reward of -1. And then it will transition to the absorbing state. And the absorbing state, the agent will not receive any reward and stay there forever. So this is how you could model a simple problem like a simple setting like the agent in like a robot moving in a maze, or you could also think of this as a setting in a game. You have a game where there are goals and there are traps. The agent needs to find out how to reach a trap, a goal as fast as possible. You can model it as a reinforcement learning problem in this way. Now, what's really important that I didn't mention yet is that um, suppose I did not have a discount factor in the problem as it currently is formulated. Well, in the way that the problem is currently formulated, there is no incentive for the agent to reach the goal quick, right? Because the agent would keep observing reward 0 when it makes its choices, 0, 0, 0, 0, 0, 0, 0. And at some point it would transition, it would move to this state, and then it would take an action and observe reward 1. So the only important thing, the only thing that the agent is encouraged to do, the way I currently formulated the problem, is that eventually it would move to this state and take an action. However, if I introduce a discount factor, then the agent is encouraged to find a short path to the goal. Why is that? Because remember that a reward observed some time steps into the future will not be worth as much as a reward observed immediately. And so if the agent wants to make the most of the reward that it's going to observe only once when it makes an action in this state, it's going to have to arrive there as soon as possible. So having a discount factor in the problem formulated like this makes it so the agent has an incentive to reach the goal as soon as possible. Now, there's a different way in which we could have formulated this problem, which wouldn't require a discount factor. We could have said, for example, that the agent would be penalized by receiving a reward of -1 on every action, except on the action that transitions into the goal, for example, and then it would move into the absorbing state after that. So there are different ways in which you could formulate this problem, but you always have to be careful that the agent is encouraged by your reward definition to do what you want it to do. And it's not entirely obvious sometimes how to formulate the rewards to encourage the agent to do what you want it to do. So I hope this example made it clear to you how a problem can be formulated as a reinforcement learning problem. Now, reinforcement learning has many applications. And so reinforcement learning has been used, for example, to teach agents to play Atari games by just receiving raw images and rewards as inputs. So many Atari games can be solved already by reinforcement learning agents. Reinforcement learning has been used to train agents that play Dota 2. Reinforcement learning is also inspired ideas behind systems that are currently the best that we have to play chess and Go. Reinforcement learning also has many applications in robotics. One flashy example is this robot that learns to manipulate Rubik's cubes. So this robot doesn't solve the Rubik's cube problem using reinforcement learning. It just, given a solution, it's able to manipulate the cube in the to make that solution. So basically, reinforcement learning here is used to transform an abstract solution, like a sequence of steps that you would have to perform on the cube. Reinforcement learning is used to transform that into a robot manipulation that actually deals with a real cube in the real world. There's also many other applications of reinforcement learning. There are applications in logistics, in finance, and marketing. So you can imagine, for example, that a reinforcement learning agent is living in an environment that is just made up of financial information, and it needs to make decisions about buying and selling stocks, for example, or it lives in an environment where it receives information about users, and it has to make decisions about which ads it should show to specific users, and so on. So there are many practical applications for reinforcement learning. Anytime you have sequential decision making under uncertainty, you can apply reinforcement learning. There are, but more interesting than that to me is the fact that every task with a computable description can be formulated as a reinforcement learning. So in a sense, every problem in theoretical computer science can be formulated as a reinforcement learning problem. And as we know, many computational problems have no efficient solution, and that does not depend on whether P is equal to NP or not. And as a consequence, because every task with a computable description can be formulated as a reinforcement learning problem, and because we know that some tasks cannot be solved efficiently using computers, then we also know that not every reinforcement learning problem will have an efficient solution. So I'm calling this the curse of generality, the fact that every well-defined problem is a reinforcement learning problem, but most reinforcement learning problems cannot be solved efficiently. So what are the problems that can be solved efficiently, and how can they be solved? That's going to be we'll talk about that in the remainder of this block. So before moving on, I want to introduce the framework of Markov decision processes to you. So in a Markov decision process, you have states that summarize the entire past with the information that is relevant to make future decisions. So if you're dealing with a Markov decision process, and a Markov decision process, you can think of it as a type of reinforcement learning problem. So in a Markov decision problems, a state summarizes the entire past such that you don't need to look back at what you did in the past to make a decision. All you need to look at is the current state, and the current state has all the information that is relevant for decision making. Okay, so the way of representing that a problem has this Markov property is to say that the probability of state st plus 1 being st prime, and the reward that you're going to observe at time step t plus 1 is r prime, given the entire sequence of interactions between the agent and environment. So the first state, the first action, the reward that you observed, and then the next state, the next action, the next reward, and so on and so on. If that probability, the probability of the next state being s prime and the next reward being r prime, given the entire history that you've seen so far, is equal to the probability of the next state, of the state at time step t plus 1 being s prime, and the reward that's time step t plus 1 being r prime is equal, if that is equal to this probability given the current state and the current action. That is, if the probability of the next state being something and the next reward being something is given the entire history is equal to the probability of the next state being something, that's something, and the next reward being that's something, given only the next, given only the current state and the current action. Okay, maybe I should explain this in a slightly different way. So one way to interpret this equality here is this. So if you can completely ignore what has happened in the past and only consider the current state and the current action to predict what state is coming next and what reward is coming next, then you have the Markov property. Okay, I hope that's clear now. Now this in a Markov decision process, the conditional joint probability distribution over states and rewards is called the one-step dynamics of the problem. And it's basically all that you need to know. So if for any state S prime, for any reward R prime, and for any state and any action, you're able to give me what is the probability of transitioning to that state S prime and obtaining reward R prime given the current state and the current action, then you have the one-step dynamics of the problem, and then you can solve the problem with the techniques that you see in this, that you see very soon. So what's an environment model? And we'll define the environment model based on the one-step dynamics of the problem. But I want you to think about environment models from a more abstract perspective first. So basically, an environment model is a description of how the world behaves. Okay. So the one-step dynamics is one way of describing how the environment behaves. So the one-step dynamics tells us what's going to be the next state and the next reward if I take a specific action in the current state, in probabilistic terms. But there are other ways to represent an environment model, and they can all be derived from the one-step dynamics. So the usual way in which we represent an environment model is in reinforcement learning is with two different things. One of them is the probability distribution over next state given each state and action. And the other is the expected reward given each state and action. Okay, so you can imagine, recall the robot here. So let's think about these things. I think I'll show you one more slide before I go back to the example and make this all very concrete. So, okay, so the environment model is this description of how the environment behaves. And having a description of how the environment behaves basically allows the agent to solve the problem in its head, in a sense. So because if the agent knows what are the consequences of its actions, it can plan all the actions that it needs to take in its head. And once it's time to interact with the real environment, the agent will be able to do to solve the environment very easily. And by solve, I mean interacting in such a way that maximizes the expected discounted return that we've seen before. So let me introduce the first step then. I said that an environment model could be split into these two parts: the probability distribution over next state given each state and action, which basically tells the agent what state is going to follow once I take this specific action in specific state, and the expected reward given each state and action. So the agent also needs to know what's the expected reward that it can expect if it's in a specific state and action. So let's look at the first step. The first step, the first part of this environment model is what we'll denote by PSS prime A. So PSS prime A is a shorthand for the probability of the next state being S prime, given that the current state is S and the current action is A. Okay, so PSS prime A is the probability of transitioning from S to S prime given action A. And PSS prime A can be derived from the one-step dynamics that you can see here in this way. But you don't need to worry too much about this. I think it's probably intuitive to you that you can derive the probability of transitioning from S to S prime with an action A from the one-step dynamics as I defined earlier. Now, it's very important to note that PSS prime A is independent of the current time step. What do I mean by independent? So let's say you are in time step t equals 0. You could write down, sorry, so you could write down, for example, the probability of the first of state 1 being S prime, given that state 0 is S and action 0 is A. But this probability would not change across time steps. So now maybe if you were at time step 10, the probability of transitioning from state S to state S prime with an action at that time step would remain the same. So that's what I mean by PSS prime A being independent of the current time step. It doesn't matter at which time step you are, the probability of transitioning from one state to another state, given a specific action, remains the same. And if you don't want that to be the case, if you want to say that things depend on the time step, then the time step needs to be encoded inside the state, okay? So then the current time step becomes important for decisions. And remember that in a Markov decision process, all that is important for a decision must be included into the state, into the description of the state. And so if you want the probability of transitioning between states to change across time steps, you have to represent that the information about the time step inside the state, okay? So these are all questions of modeling. There are many different ways of modeling a reinforcement learning problem, and you need to be really careful when you do that. So let's think about these. Let's think about our grid roll example. So let's say again that this is state 1, this is state 2, 3, 4, 5. And let's write down the PS. Let's write down the probability of transitioning between states for state 1. Okay, so the probability of transitioning, and I would denote the actions by up, down, left, and right. Okay. So the probability of transitioning, let's start with the valid actions, okay? So the probability of transitioning from state 1, this state, to state 2, with action right is equal to 1 in this environment, okay? So every time you are in this position and you take action right, you have 100% probability of transitioning to state 2, okay? And now let's look at what happens when you press down, when you go down from this position. Well, the probability of transitioning from state 1 to state 5 when you take action down is also 1, okay? Now, remember what I said happens when you take an invalid action from this state. So for example, when the agent simply will stay where it is. So how can we represent this? Well, we can say that the probability of the agent transitioning from state 1 to state 1 itself when it takes action left is 1. Because every time the agent takes action left at this state, it's going to stay where it is. And we can say that the probability of the agent transitioning from state 1 to state 1 when it takes action up is also 1, okay? Now, in order, we would need to define for every combination of state, for every pair of states and action, we will have to define these probabilities in order to fully define this environment as a Markov decision process, okay? So of course, I'm not going to go into that, but you can see that it's not something that's very hard to do. You could easily implement an interface um, in your favorite programming language to easily give you the probabilities of transitioning between states once you understand the rules of this game. Okay, so that's how you define um, PSS prime of A for every SS prime of A in that specific game. I hope the concept is clear, because it's a very important concept to understand. Um, oh, and again, why are we using probabilities here? Because we want to be very, we want this definition to be very general. So in many environments that you have, there are probabilistic transitions between states. Even though our game, the game that I was just showing, is deterministic, there are many games that are non-deterministic, right? So you can think about transitioning with probability 50% to one state and probability 50% to another state in a given situation in a game. Or you can use these probabilities to represent, for example, the result of an event that you cannot really easily predict. So maybe the agent will flip a coin at a specific moment, and you have to be able to represent that you cannot really be sure a priori where the transition is going to. Okay, so the other step so I already defined one of the things that I need in order to fully define a reinforcement, a Markov decision process, and that's the probability distribution over next state given each state and action. But there's one more thing that I need, and that thing is the expected reward given each state and action. So the expected reward, so RS prime A can be interpreted as the expected reward of having transitioned. So this is after the fact, okay? It's a little bit different than the previous one. So RS prime A is the expected reward of having transitioned from state S to state S prime through action A. So I have taken action A. That action A took me from state S to state S prime. What should be what's the reward that I should expect having seen this transition from S to S prime using A? That's what RSS prime of A denotes. So you can write it down in this way. So you can say that it's the expected reward at a time step t plus 1 of being at state S in time step t, taking action A in time step t, and having observed state st plus S prime at time step t plus 1. So also note that RSS prime of A is independent of the current time step in the same way that that I explained before. So no matter what time step you are, you should expect the same reward for having transitioned from a state S to state S prime through an action A. Okay, and RSS prime of A can also be derived from the one-step dynamics that I mentioned earlier. But this is just a small note. Okay, so the one way to represent the dynamics, the environment fully is through the one-step dynamics, and the other is through these two quantities for every state, for every pair of states and action. Okay. So if you implement a class, for example, in your favorite programming language that has a function that returns these two quantities for every state, for every pair of state and action, I will be able to apply a reinforcement learning algorithm that finds the optimum policy as long as the number of states and the number of actions is finite. Okay? And this is something that I haven't mentioned before, but the algorithms that are really efficient that we'll look at first are the ones that work when the number of states and the number of actions is relatively small. Now we need one more important definition before we move on. And I know that there are many definitions today, and I know that it's a lot to take in, but I hope that I'm able to provide a good intuition behind each of them. Okay, so let's talk about the value function, v pi. So remember that pi is a policy. Pi is that function that, given a state and an action, gives me the probability of, in that state, in that state S, taking an action A. Okay, and so the policy basically encodes the behavior of the agent. So let's say, for example, that that my policy for this agent here is, wherever the state is, always go up, right? So that's one possible policy, and you could represent that policy by saying P of S up is always 1. So no matter, for all S. So no matter the state, the probability of going up is always 1. Okay, so that's how you could represent a policy that always goes up no matter what. Now, is this a good policy? No, it's not a good policy, of course, for this game. How could we represent the optimal policy? Well, one potential optimal policy would be the policy that when it's in the state, it goes up with probability 1. It goes up with probability 1 from this state. It goes right with probability 1, right with probability 1, right with probability 1. That's one way to represent an optimal policy for this environment, okay? But there's another optimal policy, and I'll soon make very precise what I mean by optimal policy, but I think you can already guess what it is. Another optimal policy here would be right with probability 1, right with probability 1, up with probability 1, up with probability 1, right with probability 1. So these are two optimal policies for this environment. And they can both be represented by a function pi, by a certain function pi, of course, different functions pi for these two different behaviors. Okay, so going back, I want to define now what's the value function for a specific policy pi. Okay? And the value v pi of S of a state, of any state S, is the expected discounted return of starting in that state S and then following the policy pi from then on. So the value under pi, as we usually say, the value under pi of state S is the expectation. Let me use this expression here. So the value of a state S under the policy pi is the expected sum of future, discounted sum of future rewards that you observe if you start as state S and you take actions according to the policy pi. So notice that depending on the policy that you follow, you should expect to receive more or less reward. So if you use that bad policy that I mentioned earlier, where you always go up in the example environment, then you should expect a reward that's not that great. But if you use the good policy that I showed afterwards, you should expect a high sum of rewards until the end of time. So remember that's, so let's look at each of these elements here. So we have an expectation, and this subscript here by pi simply is here to make it clear that the decisions are being made according to pi. So the probability of taking a specific action in a given state is given to us by pi. That's what this subscript here denotes. So we have this expectation under the policy pi of starting at a time step t at state S of the sum of rewards that you can expect after time step t. So it's the sum of rewards, of discounted rewards, rt plus 1 plus gamma rt plus 2 plus gamma squared rt plus 3, and so on until the end of time. Okay, and we know that this sum converges because we chose gamma lesser than 1. Okay, so that's the value of a state. So what's the interpretation here? Well, the value is basically represents how good a state is under a specific policy. So notice that a state may be better or worse depending on the policy that you're following. So for the same state, you can expect more reward if you are acting according to a good policy than you can expect if you are acting according to a bad policy. That's very important. The value function is always dependent on a policy. The value of a state always depends on a policy. Okay, so we have now to go through the definition of the action value function. So the action value function is very, very similar to the value function. So let's see it. The value q of pi of a pair of state and action is the value of taking the action A when in state S, and then afterwards following the policy pi until the end of time. Okay? So the idea here is that q of pi of S and A will give us the value of taking a specific action in a specific state, basically ignoring what the policy tells us to do, but then afterwards following the policy. Okay? So this is a way to evaluate a specific action in a specific state, the value of taking a specific action in a specific state and then following the policy, instead of just evaluating what is the value of the current state under the policy. Okay, so let's look at it once more. So the action value of state S and A under policy pi is an expectation, considering that we will make decisions according to policy pi, of the sum of discounted rewards until the end of time, given that our current state is S and our current state, and the action that we took in that state is A. So in state S, I'll take action A. What is the return that I should expect to see from now until the end of time if after having taken this action, I'll follow the policy strictly? And as I said, the value function and the action value function are very similar. And you can actually relate one through the other through this expression. And I'll call this theorem the recursivity of the value function. Okay. Oh, actually, this is not the theorem that I had in mind. This theorem just shows that that there is a recursive definition for the value function. We'll see later the theorem that I was mentioning about the relationship between V and Q. So forget about that. So it's really interesting to see that the value function has a recursive definition. So let's look at this recursive definition. So for any policy pi that you have, so for any function that you can come up with that represents how the agent behaves, and for any state, the following holds. So the value of a state S under the policy pi is equal to the following.
it's equal to the sum for all actions of the probability of in a specific state taking that action times this quantity here. So first of all, notice that this is an expectation over is a conditional expectation over action. This is basically saying that the value of a state under the policy pi is a sum of the probability of taking each of the possible actions under that state. So here you should probably expect the reward that you should, this is basically an expression for the return that you should expect to see after you take that action in a specific state. And this is what it represents. So the value of a state under policy pi is the sum for all actions of the probability of taking a specific action for that state of the sum over all other possible states of the probability of transitioning from your original state to that new state when using the action uh, from the previous expectation times the uh, immediate reward that you should observe on transitioning from state S to state S prime, given the action A, plus a discount factor times the value under the policy pi of the state that comes later. So I know this is quite a mouthful. So let's think about a little bit about it one more time. So the value of a state under a policy pi is an expectation over the actions that you would take at this state according to the policy pi, of an expectation of where those actions would take you to, uh, um, over, over, over an expectation of where those actions would take you to, of the immediate reward that you would observe if you were taken to each of those new states, plus the reward, the discounted return that you could then expect to obtain from the states that you transition to. So I hope that this is at least somewhat intuitive. So basically, the value of a state is depends on the immediate reward that you can expect to see, plus the reward that you should expect to see from the next state onwards. Okay?